Okay, welcome to the review for the chapter on carboxylic acids and esters. This is actually chapter 14. Alright, you should know how to name these compounds, and not only the common names, but also the IUPAC names. So here's the common names for the first four acids. Formic acid is the common name. The IUPAC name is methanoic acid. Remember, methane would be the alkane. And what we do is we will drop the E and add oic acid, so methane becomes methanoic acid, the common name formic acid. Structure here, simple 1 carbon acid. The C double bond OOH, this is a carboxyl group. Okay, then on here it says understand the physical properties of the carboxyl group. All acids, by virtue of having this carboxyl group, are defined as acids. So we can just, this is known as the carboxyl group. Acetic acid, 2 carbon acid, would be ethanoic acid. Ethane is the 2 carbon alkane. We drop the E, add oic acid, ethanoic acid. Structure here, you can draw it in a slightly different way. You might see it drawn like this. If I draw it as I did the other one, it'll look like that. Propionic acid, the common name for propanoic acid. Propane, drop the E, add oic acid, propanoic acid. Butyric acid, common name for a 4 carbon acid. Butane is the alkane. Butanoic acid is the IUPAC name. 1, 2, 3, 4. So draw the skeletal structure like that. Understand the physical properties of the carboxyl group. Carboxylic acids have the highest boiling point and solubility compared to any of the other compounds of a similar molecular weight, compared to, put it over here, any other compounds of a similar, I just say size. When I say size, I'm really talking about molecular weight. And part of the reason for this is, well, of course they have that OH, that hydroxyl group, so they form hydrogen bonds, but they also form these dimers. So I will draw structure of, say, acetic acid. We'll make 1 blue and 1 purple. And the hydrogen bonds are these through space interactions. Remember now, oxygen will have a partial negative, hydrogens have a partial positive charge. Okay, so they form these dimers. And carboxylic acids, first off, they're all liquids at room temperature. Some are kind of volatile, but they're still all liquids at room temperature. And lower molecular weight acids, what can we say about them? They're all soluble. I shouldn't say all soluble. They are soluble in water. That's less than or equal to 5 carbons. They also have strong odors. recognize these key reactions. First, we have the ionization reactions, or this reaction with water. Sometimes this is also referred to as hydrolysis, but it's not like the hydrolysis of an ester that we'll be talking about later. All we're doing is reacting this acid with water, and the carboxylic acid, right here, carboxylic. It's a carboxylic acid water. It ionizes and produces hydrogen ions, and the carboxylate ion. So acetic acid becomes the acetate ion. Ethanoic acid, all right, remember ethanoic acid is the IUPAC name for acetic acid. This becomes the ethanoate ion. So you can see here with the carboxylic acid, what we do is we drop the ic acid part and we add ate ion. Right? We drop the ic acid and we add ate ion. Ethanoic acid becomes ethanoate, I should say here, ion. We draw the structure of the, draw it in a couple different ways. Right? So similar to what we have up here for acetic acid, but it's missing that hydrogen, right? That hydrogen was ionized. So we have the acetate or the ethanoate ion. Another way we could draw this is like this, right? Formic acid becomes formate. The other name for formic acid is methanoic acid, becomes methanoate. Okay, I just want to show you some others that you might be familiar with. There's an acid we'll be talking about later, citric acid. Becomes the citrate ion. Lactic acid becomes the lactate ion. Glutamic acid becomes the glutamate ion. You might be familiar with glutamic, or rather glutamate in terms of monosodium glutamate, or MSG. Right. Salt formation, the addition of a base. And acid plus salt, acid plus base gives you a salt plus water. So if we were to add, let's use benzoic acid. We did this reaction in the lab. Right. So here we have benzoic acid, and we'll use the base sodium hydroxide. The salt we get, what happens here is the sodium displaces the hydrogen. The hydrogen replaces or displaces the sodium. And we get sodium benzoate, the salt. Right, so the benzoate ion is an anion, it's negative, and the sodium ion, positive, plus water, of course. I'll write water as HOH. Right? So this hydrogen displaces the sodium, right? And you get HOH, or water. And when we name these, now remember we name, with salts we always name the cation first, so it's sodium and then the anion. So first the cation and then the anion. What is the name of this anion? Well, this was benzoic acid. We drop the ic acid, we add ate, so this becomes sodium benzoate. Ester formation, addition of an alcohol, also known as esterification. So we're going to take an acid, say acetic acid, and an alcohol methanol, and we get the common name would be methyl acetate. And actually, let me just underline. All right, the acetate comes obviously from acetic acid, and the methyl part, right, comes from methanol. Let me go ahead and draw the structure. Actually, before we do that, let's talk about the IUPAC name. The only difference between the common name and IUPAC name is acetic acid is also known as ethanoic acid, so this would be methyl, so this would become methyl ethanoate. What is the structure of this? Well, let's start with the acid, acetic acid, or ethanoic acid. Right? There's the ethanoate or acetate ion, and to that we will essentially replace the hydrogen with the methyl group. Okay. So in blue here, the methyl, right? And what's the name of this ion? Well, that's a 2-carbon, comes from the 2-carbon acid, so methyl ethanoate. Formic acid and ethanol. Oh, by the way, right, just as when we name salts, we name the cation first. The anion, if you wish, is kind of like this. You can, now these guys don't ionize like an acid does, but just as we have the ethanoate ion, that comes last, and the alcohol is named first. So ethanol will give us an ethyl group, right? And formic acid gives us formate. The IUPAC name for formic acid is methanoic acid, so this would be ethyl. This would be ethyl methanoate. So let's draw the structure of methyl ethanoate. Ethyl group. Right, there's an ethyl group. We're going to attach this to a 1-carbon, essentially comes down to a 1-carbon acid, and so we have the carbonyl from the acid. Okay, and this carbon now has 4 bonds, right? So there's just a hydrogen attached to here instead of another carbon. So this is the methanoate. Oops, I almost forgot the oxygen. Let me clean that up a little bit here. We should have the oxygen. There we go. So this is our ester. Ethyl group comes from ethanol. The methanoate, here's the methanoate ion, if you wish, comes from methanoic acid or formic acid. The ester linkage, now when you're looking at esters, it doesn't matter which way I draw it. You have a carbonyl carbon attached to an oxygen, and this oxygen now can't be to a hydrogen, it's got to be to another carbon. Okay, so this is essentially the ester linkage. It doesn't really have a formal functional group name. We just refer to this as the ester or the ester linkage. It's a G, linkage. If this was a hydrogen over here, then it would just simply be an acid, but we replace the hydrogen of the acid with an alkyl group. Right? So either methyl, ethyl, propyl, isopropyl, butyl, octyl, whatever. Okay. Properties of esters. Here we're talking about the physical properties. Down below we'll talk about the chemical properties. If you remember when we made these esters in lab, they separated from the water, so in terms of solubility they're slightly soluble, but essentially the main thing to remember is they're less soluble than the acid or alcohol that was used to form them. So less soluble than the acid or alcohol. Acids are the most soluble, the most polar. Esters are on the order somewhere around the polarity of an ether. So they're slightly soluble in water, but not nearly as soluble as an acid or an alcohol. They're also less dense. If you remember, we made these esters in lab in our test tube, and you had a tiny little ester layer on top, and on the bottom we had the acid and the alcohol. Okay. Boiling points, if you remember, a lot of these esters, well, we can talk about the odor as well, but these esters had pronounced odors, and part of the reason for that is they're volatile. They evaporate easily, and we can detect them with our nose. When we smell that odor from the ester, we're essentially breathing in the vapors of that ester. So they're going to have, they're less polar, of course, so they're less soluble. They also have lower boiling points. They do form hydrogen bonds with water. I should point that out. They do form hydrogen bonds with water. Right? Because actually we can put a water molecule right here. And we can form a hydrogen bond between the hydrogen of a water molecule and one of the oxygens of the ester. But there's no hydrogen here in an ester linkage, so they do not form hydrogen bonds with each other, so they're going to have lower boiling points. So do not form H bonds with each other. pH, essentially the pH of these guys is going to be neutral. Right? Acids, of course, have that acidic hydrogen, but we've removed that and essentially replaced that acidic hydrogen with an alkyl group. Right? This is, let's look here. If this is the acetate ion, if there was a hydrogen here instead of a CH3, it would be acetic acid. We replace that with the CH3. This bond is now not as, well, acids donate hydrogens. We don't have a hydrogen here, so it's not going to be acidic, it'll be neutral. And the odor, I'll just say, are often pleasant odors, as we learned in lab. Okay. Ester hydrolysis. Okay, this is essentially the reverse of the esterification reaction. And I should point out, esterification is catalyzed by acid. So I'll put a hydrogen ion on the reaction arrow there. Ester hydrolysis is just the reverse. We're going to take this methyl acetate, split it apart, and we get acetic acid and methanol. So this is essentially the reverse of esterification. Okay. Ester hydrolysis will give us the carboxylic acid and the alcohol. So a specific example here, we can use methyl acetate again. So here's our methyl acetate, same guy is up here. And what we're going to do is essentially split this guy down the middle, break that apart. We do that by essentially adding water across there. Again, this is catalyzed by hydrogen ion, or the acid. And what we end up getting is the carboxylic acid. Okay. So it's the addition of, it says the addition of acid. Essentially, it's really the addition of water. Put here, it's the addition of water, but it is catalyzed by an acid. So if you add acid to a solution of, if you add like HCl to a solution of an ester, it will hydrolyze. You would put one of the hydrogens on here to give us the acid. and put the OH on here to get the alcohol back. So it's hydrolysis, splitting apart by the addition of water in one direction. In the other direction, we take the acid, carboxylic acid, and the alcohol, catalyzed by, I just put here H+, but it's, I think in the laboratory we used HCl. Going in the reverse direction, it's esterification. Okay, now the next one, ester saponification. We're going to split that ester apart, but this time by the addition of a base. All right, ester saponification, addition of a base. You can also think of this as soap making. Later on in the laboratory, we will use this reaction to actually make some soap. What happens here, again, let's start with methyl acetate. So there's our acetate. Here's our methyl group. We're going to break this apart, but we're going to use a base like sodium hydroxide or potassium hydroxide. So we split this guy like that. And there's actually a couple ways to think about this. I'm going to do this in two ways, actually. Let me turn this blue so you can see it a little bit better. Okay. The sodium hydroxide, the sodium forms the salt with the acid, and the hydroxide is attached to this methyl group to give us the alcohol. So we end up with, instead of the acid, we end up with the salt of this acid. In this case, the sodium salt, so sodium acetate, plus methanol. So we have a carboxylate salt plus the alcohol. In this case specifically, the carboxylate salt is sodium acetate and methanol. So that's one way to think about it. The sodium is positive, so it neutralizes the negative charge on the acetate ion, right? And the OH forms the alcohol. That's one way of thinking about it. Another way is thinking, well, okay, I'm going to split this apart, and I'm going to get, just as we did before, let me put it over here, we get, say, acetic acid plus methanol, just as we did before. But remember, of course, now this reaction arrow doesn't mean these reactants are going anywhere. These reactants are converted to products, but the products here are still in the same reaction vessel as the sodium hydroxide. So what do we know happens when we have an acid in the presence of a base? Well, an acid and a base makes a salt. And water, right? So we get the carboxylate salt. So it's kind of, you can think of it as maybe two steps. First, you split it apart to get the acid and the alcohol, just as we did above with the acid hydrolysis. But because that acid is in the presence of this base, you get this acid-base reaction to produce the salt. All right, identify the uses of carboxylic acid salts. I mentioned in class sodium benzoate is a food preservative. I won't draw the structure of monosodium glutamate, MSG, or monosodium glutamate. Right, this is the sodium salt of glutamic acid, and these are used as food preservatives, and also flavorings or flavor enhancers, maybe. Qualitatively relate the pKa of carboxylic acid to its ionization state of various values. Alternatively, you could use the Henderson-Hasselbalch equation. We used that way back in chapter 8, and that kind of goes along with number 5 down here, carboxylic acid buffer works. We did not talk about either of these in the lecture, but I do. We did actually do something like this in lab. Number 4. Number 5, I'm just going to omit, but we can look at number 4 here. Okay. First off, this question mark should be an equilibrium arrow, but something got messed up with the font here. So an acid ionizes to give us a conjugate base and the hydronium ion. Right. So let's use, we actually did this with 2 different acids, benzoic acid and acetic acid, and I'm just going to use benzoic acid because it's a little bit more fun to talk about. Right, so here's benzoic acid. Now benzoic acid, right here's the acidic hydrogen, and it will ionize. It will give us the benzoate ion, which is its conjugate base, plus, now I have here the hydronium ion. That would be if we had water as one of the reactants in a Bronsted-Lowry sense. So what do acids do? They donate protons. This acid donates a proton to water, H2O, forming H3O, the hydronium ion. But I'm just going to write it as H+. We learned back in chapter 8, H3O, the hydronium ion, and the hydrogen ion, or a proton, are essentially the same thing. All right, so this is the benzoate ion. And what this is talking about is relate the pKa of a carboxylic acid to its ionization state. The pKa you can kind of think of as a balancing point. And actually, let me just define Ka first. Again, Ka is going to be it's essentially a ratio of products over reactants, and this is the concentration of the products over reactants. So in terms of this reaction here, we would have conjugate base and hydrogen ion divided by the carboxylic acid concentration. pKa is really nothing more than like pH. It's the negative log of the Ka. So the Ka is a value for benzoic acid. I believe it's something like 6.5 times 10 to the negative 5th. Something about on that order. And the pKa then is going to be around 4.5. Right? Remember, the negative logs are exponents. Here the exponent is -5. Now it's not going to be -5 because of this coefficient of 6.5, but it's going to be somewhere near 5. So we'll say about 4.5. I didn't actually do the math, but I'm guessing that's about what it's at. All right. So if we have a pH that's lower than 4.5, again, you can think of teeter-totter here. The pKa is the balancing point, 4.5. If we have a pH that's lower than that, okay, what that means is we have more hydrogen ions. Right? Lower pH means greater hydrogen ion concentration, which means we're going to favor the benzoic acid. So this is when the pH is less than the pKa. Essentially, we're putting in hydrogen ions, excess hydrogen ions, and driving this reaction back to the left. I'll fix this a little bit. Okay. The benzoate ion, right, this is favored when the pH is greater than the pKa. So if this is a pKa, say it's 4.5. If the pH is greater than that, say the pH is 8 or something like that, the right-hand side is going to be favored. And over on this side, and the pK is kind of the balancing point, 4.5. If the pH is less than that, say it's pH equals, say, something like 2, okay, the left-hand side is favored. So why is that? Well, at a pH higher than 4.5, right, essentially what we're doing is if it's a higher pH, we have a lower hydrogen ion concentration. So if we remove hydrogen ions, we talked about the Chastellaer's principle back when we were talking about how buffers work, right? And the Henderson-Hasselbalch equation and all that. When we remove something on the right-hand side, it pulls this equilibrium over to the right. Now we saw this in lab. We put benzoic acid in a test tube and we shook it up and it didn't dissolve very well. So this is only slightly soluble, and you probably didn't even notice much of it go into solution at all, but if you tested the pH, it would have been acidic because a little bit of this went into solution. It's not very soluble. Why is that? Well, it's greater than, it's actually 7 carbons, right? So if it's 5 carbons and less, it's soluble, but as the number of carbons gets bigger and bigger, the solubility drops off. So benzoic acid is not really all that soluble. The benzoate ion, when we added sodium hydroxide to this, we actually removed, if you wish, we removed hydrogen ions by adding sodium hydroxide. Those hydroxide ions combined with the hydrogen ions to make water and put the equilibrium over to the right. And we ended up actually making the sodium salt, which is soluble. So benzoate ion, it's an ion. It's got a negative charge, so this is soluble. So one of the reasons you see something like sodium benzoate used as a food preservative and not simply benzoic acid is because the benzoate ion is soluble. And then we also drove this reaction back the other way by adding HCl and adding more hydrogen ions in the form of hydrochloric acid and pushing it back this way and precipitating the benzoic acid. So that'll do it for this chapter on carboxylic acids. And there's certainly more detail in the lecture. The